bullet of mass m is fired upward from the surface of a planet of mass big M and radius r. What minimum speed must it have to escape the planet's gravity? This is known as escape speed or escape velocity. And that's something that comes up from time to time. So to escape the planet's gravity means that it can keep going forever, basically. It won't fall back to the planet's surface, which means it just barely has enough speed to, so that means it can get out to infinity, basically. So it can, its final potential energy will be 0 when it has speed 0. So we can use conservation of energy to figure this out. ME initial equals ME final. At the end, we want it to be an infinite distance away, and we want it to just barely make it there so that it'll have speed v. So this is where the total energy is equal to 0. So what's our initial energy? 1/2 mv squared minus g m over r. This r is the radius of the planet. So doing some algebra, we can go like that. The mass of the bullet cancels out. So our velocity is 2gm over r square root. This is escape velocity. I starred this. This is another one that would be useful to note. Now I want to note a difference here. Escape velocity, this is the radius of the planet. The total mechanical energy of an object in a circular orbit, this is the orbital radius, not necessarily the radius of the planet. Keep in mind that those are two different things. So this is the total mechanical energy of an object in an orbit. So we couldn't use this formula to plug in for the total mechanical energy over here because this bullet is not in an orbit. It's just traveling upward. Yeah, just some, this is all related to gravitation and orbits and whatnot. Some interesting information. This isn't something you'll need to know on the exam, but it's just interesting. Black holes, the definition of a black hole basically is that there exists some point near the black hole, near the object, where the escape velocity is greater than c. C is the speed of light. So light can't get out from beyond this point, which is called the event horizon. The event horizon is it's a sphere, but this sphere is where the escape velocity becomes greater than c. At any point inside that, escape velocity is greater than c, the speed of light. So light can't get out. Because light can't get out, we can't see them directly. So looking up in the sky, if there was a black hole near Earth, you wouldn't see the black hole. You would just see darkness, which is what you see in a lot of the sky anyway. So then the question becomes, how do we detect black holes? There are three main ways that we can detect black holes. One, gravitational effect on nearby objects. So if you've got a star that's orbiting around something and you look at the middle and you don't see anything, well, maybe there's a black hole there. So that's one way that we can tell black holes are there. Another way is what's called gravitational lensing. So due to effects that we haven't learned about yet, what's called general relativity, the black holes actually bend light. So if you're over here and a black hole's right here, and there's some star that's directly behind the black hole, the light from the star will go off as it goes near the black hole to get bent, And so you kind of see double images, and this is a sphere, so it's not just double, but you see this kind of spherical repetition of the objects behind the black holes. So that's another way we can tell. Another way is via X-ray emission, not of the black hole itself, because light can't get out, but X-ray emission of nearby objects. So as objects are pulled into the black hole, the gravitational force puts it under a lot of pressure, and they radiate X-rays. And actually, there's another way, detecting what's called Hawking radiation. So, due to quantum mechanical effects that are beyond what I really understand even though the escape speed of a black hole is greater than the speed of light, quantum mechanics is weird, and particles are emitted from black holes, from inside of black holes, gradually over time via a phenomenon known as Hawking radiation. So you can detect that radiation. The other effect that has to do with gravitation are the tides on Earth. So normally, here we've got Earth, and the Earth has water around all of its surface. So this is the water in the oceans and whatnot. So we've got the moon right over here. The tides are caused by the gravitational pull of the moon, and more specifically, it's by a difference in the gravitational pull from the moon. So we know that gravitational force or gravitational field either are proportional to 1 over r squared. So that means as you get farther away, the gravitational effect becomes less. So the gravitational field is stronger at points on the near side of the Earth, which means that the water in the ocean is pulled toward the moon, creating a high tide over here. And meanwhile, over on the other side, the pull on the Earth, the gravitational field acting on the Earth is stronger than the gravitational field acting on the water over here. So the Earth is kind of pulled away from the surface of the water over here, creating a high tide over there, while at these points that are at right angles, there's no difference, and the water just stays where it would naturally be anyway. Well, would stay where it would naturally be anyway, but some of it is pulled to flow over here. So at points that are on the line between the moon and the Earth, you get high tides, both on the side facing the moon and on the side that is opposite the moon. And then at the points that are 90 degrees away, you get your low tides. So that's how tides. That's why tides happen. They're a difference in the gravitational field from the moon between the two sides of the Earth.